Yeah. So, so this is called as the main sequence, mainly because stars spend most of their lifetime on this locus. Okay. And then there are like three major areas outside of this. Here you have giants. Here you have supergiants. And here you have white dwarfs. Okay. Now we will go into a little more details about the structure of the HR diagram. But what you see here is a sequence in mass. So the lowest mass stars will be at this end, and the highest mass stars will be at that end. Do you think this represents purely the Stefan Boltzmann law? There's a drop off there. It's not exactly parallel, but remember there are two parameters in the Stefan's law. One is the radius, one is the luminosity. Okay. So sorry, one is the radius and one is the temperature, and both of these are changing systematically along this curve. So the reason it is not a straight line, and it goes here, it is sort of near the 1 solar radius. Here it is at the 0.1 solar radius. And over here it's at the 10 solar radius. So the radius is also changing. That is why this thing is not a straight line. But every star, every main sequence star follows the is essentially a black body. And therefore, since it's a black body, it has to follow the Stefan Boltzmann relationship. Except that neither temperature is constant nor is radius constant. They're correlated. And that is why you get this very, very clear sequence, which is known as the main sequence. What causes stars to leave the main sequence? Yes. So when it runs out of fuel, okay, when it runs out of fuel, the star begins to move. It does very, very different things than what it is normally doing. So the sun, for 10 billion years of its life, is going to be very, very stable main sequence star, just sitting here, barely moving from its position. And then over the next 500 million years or so, it's going to do one full chakkar. We will see what exactly it will do in a minute. Okay. So many stars, many low mass stars go through a giant phase. And the sun will also go through a red giant phase. So the sun is going to go and sit in this part of the diagram for a short duration of time. Where will it eventually end up? White dwarf. So it's going to come here eventually. The sun has too less mass to ever become a supergiant. So sun is never ever going to become a supergiant. It's going to go from here, it's going to go there, and it's going to come down. So we will look at the HR diagram again in more detail in a few minutes. Okay. But there's one more thing that I wanted to point out over here. So there's a number written here, lifetime 10 raised to 7 years. So if a star is sitting here, it only has a lifetime of 10 raised to 7 years. It's going to move off the main sequence after that. Here, lifetime is 10 raised to 8 years. Over here, it's 10 raised to 9 years. Here, it's 10 raised to 10 years. Okay, that's the lifetime of the sun. And here, the lifetime is 10 raised to 11 years. And here, it can go even longer. So, 10 raised to 11 years is already 7-8 times the lifetime of the universe. So stars which are in this part are going to live forever, essentially. At least 10 times more, 20 times more the current lifetime of the universe. very long-lived stars. So this, why do you think this kind of sequence exists? Why do massive stars live for a short duration? Hmm? Yes, that is correct. But it also has a larger amount of mass. So what has to happen is that the luminosity has to scale as some high power of mass. So you will see that for the most massive stars, luminosity goes as mass raised to 3.5. Okay, so it burns up its hydrogen very, very quickly. So although it has more mass than, say, the sun, it may have 30 times the mass of the sun. But if it is 50,000 times brighter, then that's not going to buy much time, right? So that is why the lifetimes are short over here and why they're long over here. Right. So this is the locus of the sun. So this is our main sequence. Okay. Remember, the main sequence is also a sequence of color. Okay. The O-type stars are all going to be here. The M-type stars are all going to be here. You have it labeled like that over here. And this is on some scale, the luminosity. I think it's absolute magnitude. And what's happening here is the sun is going to quietly sit here for 10 billion years. Then it's going to move to the red giant phase. Then it's going to do a sequence. So here it's going to be part of something known as the horizontal branch. Okay. And when it becomes, it'll stay there for a while and then eventually come down and become a white dwarf. So we'll look at Gaia images of this in a minute. But so this is another version of the HR diagram. This is the Hipparcos HR diagram. So Hipparcos was an astrometric satellite that was launched about 40 years ago now. And it, for the first time, measured parallaxes to reasonably good accuracy. Before that, parallaxes were very bad. See, remember, measuring the color of a star is very easy. Okay, you just measure it in B, measure the magnitude in B filter, measure the magnitude in B filter, you're done. Okay, but this part is hard. This part is very hard because determining distance is quite difficult. Moment you have good parallax determining machines like Hipparcos, you can construct the HR diagram. Nevertheless, people were able to draw insights on the HR diagram even 50 years, 70 years before this diagram was actually constructed. So that just shows that, I mean, if you know what's happening and if your physical models are robust, you can make predictions about the this kind of diagram. Okay, so here you see something interesting. These white dwarfs are distributed along a curve. Okay, they don't all go and sit in the same place. Why do you think that happens? What is changing along this curve? Sorry? No, it's not almost like a straight line. Quite curved. And in fact, radius doesn't change. What's changing is temperature. Okay. So the white dwarf may originally land up over here, and then over time it will cool. And as it cools, it will become from very white kind of very high surface temperature to very low surface temperature. So it will move along this curve over time. And that can take a very long time. We'll look at white dwarf cooling curves and things like that a bit later.
The main sequence, so towards the bottom line is much more finer, whereas top to left is much more spread out. So
yes.
Due to instrumental error, so is it?
No. That is a real effect. Okay. Primarily because of metallicity driven dispersion. Okay. So many of the stars here are high metallicity stars. because what has happened is there is one generation of high mass stars which has formed. It has exploded as a supernova. It has created a large number of metals. These metals have then formed a star again. And this is now the second generation or even third generation of stars, because these are very massive stars. They go through their lifetimes in 10 raised to 7 years. So therefore, there's a dispersion. Some of them have high metallicity, some of them have low metallicity. And here what has happened is a star has formed and it's going to live forever. So once it formed, it is not releasing any metals into the ISM, nothing is happening. The stars over here are just quietly converting hydrogen to helium. Okay, they are not forming any carbon, oxygen, nothing is happening, no action is happening there. So many of them are low metallicity stars at the low mass end. And here there's a mix of low and high metallicity stars, which is creating a higher dispersion. Measurement errors will not contribute here because remember, these are very bright stars. And measuring the fluxes of bright objects is very easy. Measuring the fluxes of faint objects is very difficult. So there are no measurement errors with produced. The dispersion is real, primarily driven by metallicity differences. So what people had been doing was they'd been measuring the HR diagram for various open clusters. And why do you do it for clusters rather than random stars in the sky? Why do you do it for open star clusters?
They're roughly at the same distance.
They are roughly at the same distance. So we remember the main problem we have with determining luminosity is that we don't know the distance. Okay? But here at least we know that they're all at roughly the same distance. So you can put a distance parameter d, which on this arbitrary y-axis will not matter. And so you can even use the apparent magnitude, for example, on the y-axis instead of the absolute magnitude or the luminosity. So these are two open clusters which are quite close to us and quite close to each other also. This is the Pleiades Hertzsprung-Russell diagram. This is the Hades Hertzsprung-Russell diagram. So these kind of diagrams have been constructed for more than 100 years. But getting the y-axis right is what took us some time. Okay. So if you look at stars, the single most important parameter that determines their properties is their mass. Okay. Because if you know the mass, you can determine the surface temperature, you can determine the radius, you can determine the luminosity. And it even determines the life history on and off of the main sequence. And it determines if the star will end up as a white dwarf or a neutron star. So almost everything you need to know about the future of a star is determined by stellar mass. There are some other properties which matter. Metallicity is one of them, but it does not drastically change things, whereas this is drastically changes things. So the least massive stars are about 1/10 of the mass of the sun. And the most massive stars are approximately 100 or 125 times the mass of the sun. So there's a range, dynamic range of about 1,000 there in stellar mass. And that essentially fixes everything for you. Yeah. Where are neutron stars in the HR diagram? Good question. I was going to ask that question later. Okay. So why are there no neutron stars on the HR diagram? They don't exist. Very small in size, yes. So R is very small. Okay, so you saw those parallel lines of radius, right? So they're very, very small. So they're off the chart. Okay. Any other reason? Huh? Very low luminosity, that's right, because they're very small. They really don't have any thermal radiation to speak of. Okay, so how do we detect neutron stars? You can't determine their color. You can't determine their luminosity in any optical band. How do we see neutron stars normally? By gravitational effects, yes, but how? Surrounding of neutron stars. Not really. Okay, we will come to that. We are going to talk about these compact objects in a while. But remember, they don't exist on the HR diagram at all. Don't try to draw them on an HR diagram at any point. Okay, stellar spectrum, as we said, is basically a black body superposed with a number of absorption and emission lines. Okay, absorption lines are very, very common. Emission lines are quite rare. Usually they come from gas that is excited in the outer regions of the star, which is at high temperature. Remember, if the emission line is produced deep inside the star, we are never going to see it because the envelope will absorb it. Only when the emission line is produced outside or outer regions of the star or outside the star, that is when we can see it. So those are very rare and these are extremely common. In the case of the sun, these kind of absorption lines are very commonly seen, and then they are known as Fraunhofer lines in honor of the person who discovered. Black body is, of course, characterized by a single temperature, single number, that's the temperature. So these stellar spectral types. Okay. So the main types are O, B, A, F, G, K, and M. Where O stars are the hottest and the letter sequence indicates successively cooler stars up to the coolest M class. According to informal traditions, O stars are called blue, B stars are blue-white, A stars are white, F stars are yellow-white, G stars are yellow, K stars are orange, and M stars are red. Okay, don't take these color labels too seriously, but it's roughly a sequence. So whatever is perceived from by the observer may deviate from these colors. So people said, no, these types are too coarse, and that is particularly true for M stars, because M stars range in mass from about 0.08 solar to about 0.6 solar. Okay, and that's a fairly wide range, and their properties are very, very different. A 0.08 mass star will be very, very different from a 0.6 mass star. And therefore, you need to have subtypes. So Morgan and Keenan suggested that, okay, add one more letter from 0 to 9, indicating tenths of the range between two star classes. So A5 is 5 tenths between A0 and F0. Lower numbered stars in the same class are hotter. So A1 is hotter than A2 and A2 is hotter than A3 and so on. Also included in the Morgan-Keenan system is the luminosity class expressed by the Roman numbers 1, 2, 3, 4, and 5, which represent the width of absorption lines in the star spectrum. This feature is a good measure of the size of the star and thus of the total luminosity output. Okay, class 1 stars are the supergiants that we saw at the top of the diagram. Class 3 are simply giants, and class 5 are either dwarfs, they're called dwarfs, or more properly they should be called as main sequence stars. For example, our sun has G25. Okay, what does that mean? It's a yellow star, G type, 2/10 of the way towards orange, and it's a main sequence star or a dwarf star. So some people will say the sun is a G2 dwarf, okay, which is exactly the same. The brightest star in the sky is a star called Sirius, and that is A15. Okay, so that also is a main sequence star. Okay, one thing which I forgot to mention in the HR diagram, I'll just go back. So the brightest star in the sky is Sirius, and that is here. The second brightest star in the sky is Canopus, and that is there. So Canopus is a supergiant. It is extremely luminous. It looks on slightly fainter to us because it is extremely far away. So compared to Sirius, it is extremely luminous, but it is much further away, and therefore it looks fainter. So this we have to remember. The brightest star in our sky, whether it's bright because it's nearby or it is intrinsically luminous. There's this star Deneb, which is one of the most luminous stars known. This is moderately bright star. It's, I think, 15th brightest or so in the night sky. But it's in terms of luminosity, I think it's 10. It's more than 10 raised to 5 times the luminosity of the sun. So we can get grossly misled by distance. I mean, we do that. I mean, the sun appears so bright to us, but it's just an average star. Okay. So now the spectrum of stars can vary quite a lot. So here you are seeing a O-type star spectrum. And this is from the Sloan Digital Sky Survey. And the main feature, you see lots of absorption lines, and those elements corresponding to the absorption lines have been labeled here. You see some lines in emission. Typically, hydrogen is seen in emission, H alpha, H beta, etc. So there's the H beta line over here. H alpha line is here it's seen in absorption. Okay. So this is wavelength on the x-axis and the flux on the y-axis. And what do you notice about the spectrum? The overall shape of the spectrum. The flux is higher at shorter wavelengths, and the flux is lower at longer wavelengths. That is characteristic of the massive stars. So here if you observe the star with your naked eye, this particular star, it will look very blue to you, because in the blue filter, it will be quite bright, and in the red filter, it will be quite faint. Right? Now contrast this with a M-type star spectrum. So O-type are the most luminous, most massive stars. M-type is the opposite end, least luminous, least massive stars. And this is what you see for a O-type star. And as you can see, the flux in the blue bands, blue part of the spectrum, is very weak. And as you go to the redder part of the spectrum, the flux continuously increases. Okay? So it's the exact opposite. So these stars, if you look at it in a blue filter, it will be very faint. And in a red filter, it will be quite bright. Therefore, you will say that this is a red star. Which ones? Here? No, those are, I think these are very broad absorption lines, is what I'm guessing. And the continuum is going on top. So this is a absorption, this is an absorption, this is an absorption. So these stars cannot produce emission lines very well. Huh? That is related to the calibration. Okay, sometimes you're measuring a very noisy value, okay, and you're measuring it against with some background. So when you subtract the background, because the background also is noisy, you can get negative values. They're not physical, of course, but you can get negative values like you see here. And this may be some artifact in the data. Okay, so stars come in two main flavors. One is called population 1 stars, and the other are called population 2 stars. So population 1 stars have high metallicity. So high metallicity means greater than 0.01 metallicity. So more than 1% of the atoms are metals. What is the metallicity of the sun? I showed it to you last time. It's 2%. Okay. So something greater than half solar metallicity we call as high metallicity. So obviously sun is a high metallicity star. Its location, these type of stars are found mainly in the disk of the Milky Way, especially in large numbers in the spiral arms. If you calculate their age, they're all relatively young. Their kinematics, circular orbits around the galactic center with low velocities relative to the sun. So these are regular disk stars, like sun is one of them. Okay. When you say they're relatively young, can you put any constraints on their mass or luminosity? Their main sequence. The answer is no, you can't. Okay. We'll come to population 2 and then we'll see whether we can put constraints. Their kinematics are like this. And examples are the sun and most of the stars in open clusters. So open clusters are commonly found in the disk of the Milky Way. And this is where new stars are typically born, in the disk of the Milky Way. Okay. Now, population 2 stars. They have low metallicity, found in the halo and bulge of the Milky Way, as well as in globular clusters. So unlike open clusters which house the population 1 stars, globular clusters house the population 2 stars. So what is halo and bulge of the Milky Way? We'll come into this in more detail when we talk of galaxy morphology. But it's basically the structure. The bulge is the central protrusion that's there in the Milky Way. Okay. And the halo is a much larger structure that is spherically symmetric and surrounds the bulge. It's much fainter, of course. And globular clusters are clusters of stars that are outside of the Milky Way galaxy itself, and they are in orbit around the Milky Way, but they are not sitting inside the Milky Way. So they are like satellite clusters of the Milky Way. This age of stars, population 2 stars, is old, typically 10 to 13 billion years old, among the oldest stars in the galaxy. So once you know this, can you constrain their mass luminosity, spectral type? Yes. In this case, the answer is yes. So what will be the common spectral type for these objects? Rightmost side, that's the M-type stars. So many of these will be M-type stars, and they will all have low metallicity. Kinematics. They are in highly elliptical orbits with high velocities relative to the sun. So basically, they're not moving in tandem with the sun. They are moving in their own orbit outside of the disk. It's not a nice circular orbit in the disk, but it's some kind of elliptical orbit outside of the plane of the disk. Okay. Examples are stars in globular clusters like M13 and Omega Centauri. These are very bright globular clusters of the Milky Way. Okay, so here's a sort of comparison of these two populations. They differ systematically in metallicity. They differ in the location. They differ in age, and they differ in their kinematics.
the old stars are low metallicity. Then how did we get to the
No, O stars.
have low metallicity?
No, not O. M stars have low
Yeah, so
metallicity.
so they are the old ones, right?
Old.
Yeah.
Yeah.
So if they are the lower metallicity ones,
Yes.
how do we get to the young one which have higher metallicity? Because M stars cannot go supernova.
Correct.
They're the metals.
Correct.
So how do we get to the younger and higher metallicity?
Because there are high mass stars which have gone through many generations. The high mass stars, take a O-type star. Okay, it's going to explode and go supernova in 10 raised to 7 years. Low mass stars are just getting started in life in 10 million years. These guys have gone supernova and they have polluted the ISM from that. So any star, a second generation star that forms from that polluted interstellar medium, polluted meaning having a lot of metals, not in the human sense of pollution, but yeah, which are polluted with metals. Those metals will then get trapped inside the star. This is exactly what has happened with the sun. So the sun cannot be a first generation star. It has formed from material that has been created by the supernova explosion of an older O or B or A type star. And that is what is leading to its high metallicity. That's the reason you have. So also see the population 2 stars are long lived and they're old because the young population 2 stars, there must have been young population 2 stars, right? Okay, they don't exist anymore. They're gone. They're dead. And young population 1 stars exist because they're born much later. So the sun, for example, if it were 12 billion years old, there would be a problem with its metallicity. But because it is 10 billion years old, in the first 3 billion years, sufficient metals got created to produce stars like the sun. These are the main differences between the two populations. Metallicity is important because metal-rich environments lead to faster cooling of gas clouds, aiding in star formation. So one of the things that prevents star formation is cooling. Unless you can cool the atomic gas into molecular gas, you cannot achieve high enough densities to form the stars. So therefore, cooling is quite an important phenomenon, and the presence of metals aids in cooling. So the first generation of stars may take a long time to form because there are no metals. But the next generation of stars could form fairly rapidly because now the ISM has a lot of metals. Stellar evolution. Higher metallicity influences the lifetime and evolution of a star. So in general, if you take 2 stars which are otherwise identical, okay, they have the exact same mass. Only difference is one has, let us say, 0.01% metals and one has 4% metals. Okay. The one which has 4% metals will have a much efficient way of will have much more absorption in the atmosphere due to the presence of these metals, and therefore the luminosity of the star will change because that will determine the radius, the hydrostatic equilibrium, everything. So the luminosity of 2 stars which are identical otherwise but have different metallicities will be different. The population of POP1 and POP2 stars here helps us trace the stellar mass buildup of the Milky Way. Okay. So now this is a couple of interesting statements here. Domination of light and mass. Population 1 stars which are young. In such cases, in young stars, so take a cluster, for example, which has formed, just recently formed, yesterday it has formed all the stars. and it has a mix of both low mass and high mass stars. In such a situation, which stars will dominate the light? The high mass stars, correct? Because the massive stars, these are going to dominate the light, because we told you that there is a very strong dependence of luminosity on mass. So higher mass stars, even if it's 10 times more massive, it may be 1,000 times more luminous. So massive stars dominate the light. Low mass stars dominate mass. Okay, now why is this? This we will see later is due to the fact that when you form stars in a cluster, you don't form high mass stars and low mass stars in equal numbers. Okay? You form them in unequal numbers. And which type of stars you think will be more common? Low mass stars. Low mass stars will get common and much more common. Okay? And therefore, even if you have formed all the stars yesterday, you may have formed one O-type star, but you would have formed then 100 M-type stars or 200 M-type stars. So M-type stars will dominate the mass. Huh? I mean, this kind of power law distribution is seen in almost any phenomenon. Okay, if you take earthquakes, for example, powerful earthquakes will be common, or less powerful earthquakes will be common. Less powerful earthquakes are common. Powerful earthquakes are extremely rare. Okay. So this kind of distribution is commonly seen in nature, and as always in astronomy, this happens to be a power law. Okay, so that is known as the initial mass function. So it's simply more easier. I mean, even if you count raindrops, okay, just measure the sizes of raindrops. Will smaller raindrops be more common or larger raindrops be more common? Smaller raindrops are more numerous, right? So I don't know whether there is a sort of philosophical reason for this, but look at it from the star formation point of view. Low mass stars require you to accumulate a small amount of mass in one region, which is easier than accumulating a large amount of mass, right? And therefore, once you get enough mass to form a star, low mass star will form off. You need special circumstances that a lot of mass has accumulated, but it has not converted it into low mass stars. This is also related to fragmentation. So these molecular clouds, when they form, they tend to break up. So if one cloud forms, the probability of forming a really giant single cloud is very small. The probability of it fragmenting and forming, let's say, 100 smaller clouds is much higher. Therefore, it just goes on increasing. So low mass stars are much more common when they're formed. What happens with population 2 stars? How can population 2 stars become bright? At the end of their life, and therefore giants dominate the light. So they become so much more bigger that they dominate the light, and main sequence stars dominate the mass. And these will be all at the low mass end. So again, low mass stars dominate, but these are all on the main sequence. So are these, but low mass stars will dominate. What are population 3 stars? Have you heard of them? Primordial stars. That's absolutely right. So the first stars that form. How are they different from the stars that from the population 1 stars that we are forming today? They will have very low or no metals, right? They won't have metals. And Therefore, they will form a population of their own, because we said metallicity is an important element in star formation. So these are the first stars that formed. These are the ones that are the high mass counterparts, or the high luminosity counterparts of the low mass population 2 stars that we see today. So they formed 10, 13 billion years ago, but they're not alive today because they went supernova and disappeared.
Very low mass population.
Some of them might, some then no, you'll call them population 2 stars, right? Because they formed early on. Early on, they must, like when the first stars formed, they would have formed both massive stars and non-massive stars. The population 3 stars refers to that entire population, but you only see a subpart of that population. What will you see? You will see the most luminous of those population 3 stars, because the massive stars dominate the light.
Mistake for population 2 star for a population 1 star, because during its lifetime, it starts accumulating metals.
Yes. Inside it, does it? Tell me. Is the sun accumulating metals inside it?
Not right now. Does it not?
Has it accumulated 1 gram of metal in the last 5 billion years?
Right.
Hydrogen to helium. Helium is also a non-metal. So the metallicity of the sun is absolutely unchanged right now. Yeah. Can it change its metallicity somehow in the red giant phase? After hydrogen fusion stops, two things will happen. One is that the outer hydrogen envelope will get expelled at some point during the red giant phase. And more importantly, helium fusion will happen for a short time. So the higher elements will get formed. So although the sun will not go supernova, it will increase its metal content towards the final years of its life. That's the only time so long as it's on the main sequence, its metal content is not changing. Right? Okay. So the search for population 3 stars is a big race in astronomy. And the James Webb Space Telescope has been designed so that it can detect these population 3 stars. And radio telescopes like the Square Kilometer Array have been designed so that it can detect the complementary hydrogen. So wherever you don't have population 3 stars forming, you should have hydrogen, neutral hydrogen, and that will be detected using radio telescopes. And the stars themselves, as they are forming, will be detected by the Webb. Okay, so now we go on and talk a bit about variables. Because these are very interesting stars and there is great variety in them. This is not a course on variable stars, so I will only give you a sort of flavor of variable stars. I will not get into details. There are 2 types of variables. One are called intrinsic variables and the other are called extrinsic variables. Did you have you encountered any example of extrinsic variables? Any star whose flux changes because of external factors? Transits, extrasolar planet transits, that's correct. So you have already encountered extrinsic variables. We will look at intrinsic variables in a few minutes. Now this transit idea, of course, can be generalized to 2 binary stars going around each other. Or a normal star going around white dwarf, or many other combinations. So, so we will not talk much about the extrinsic variables. We will focus on intrinsic variables. And for about 100 years or so, there is a amateur astronomers association called APSO. It's association of American Association of Variable Star observers. And these people painstakingly, they go out on every clear night and they measure the brightness of variable stars. Very, very interesting area. See, but this is the only way we have lots of data over long time scales on variable stars. Okay, so variable stars were discovered a long time ago. There are a few variable stars in the sky, which vary quite observably. Over human lifetimes, they vary quite a lot in brightness. So people knew that these stars exist. And then there was a debate on whether it was intrinsic or extrinsic. This was mainly driven by an urge to explain all variability in terms of a single model, some kind of grand unified theory of variable stars. Okay. And a lesson here is that sometimes the search for simplicity can lead us on the wrong track. Things should be simplified as much as possible, but don't overdo it. Only in the 20th century, of the advent of spectroscopy and quantum mechanics, was it realized that there are many classes of variable stars. Now, there is something known as the general catalog of variable stars. There are 88 categories of variable stars in that catalog, okay, including 34 kinds of pulsating stars. So, obviously, this is a major lesson. Don't try to simplify things. Things are so bad that this is what a variable star tree looks like. Okay. So some of them, of course, not even stars, they're asteroids, they're rotating or eclipsing and so on. But within the stars also, there are so many categories. And for 200 years, people were trying to combine these into one. So there is no grand unified theory for variable stars. The intrinsic ones are very, very diverse. Okay? And we will look at one or two of them. So again, here Gaia comes to the rescue, because before the advent of Gaia, we knew less than, I think we knew about 500,000 variable stars or so. That has gone now to 10 million. So there has been a dramatic increase in the number of variable star systems. Okay. Lots of binary star systems have also been found. So there will be, some of these will be part of the extrinsic variables. Okay. Right. So now, because we have accurate astronometry, we have luminosity measurements, we have color measurements, and so on. So using Gaia, we can construct now densely populated HR diagrams. In the old days, I showed you the Pleiades and Hades HR diagrams. There were like 100 points there. Okay. Here, you probably have 1 billion points. And so the main sequence is clearly seen. Dwarf stars, this is where the sun sits. Okay. This is, these are the white dwarfs. Okay. And this is a sort of cooling sequence. So the young white dwarfs will all be here, and the oldest white dwarfs will be there. Then there is this giant branch. So we saw that the sun is going to become, go along this asymptotic giant branch and climb up this. As its radius increases, its luminosity increases. And why does it move to the right? Radius increases, but only up to a point. Then what happens? As the radius increases, simultaneously as the radius is increasing, what is happening to the temperature? It is decreasing. So it can, so the radius may continue to increase, but the temperature decreases pretty fast. Okay. And therefore, you get a sort of flattening or even a slight going down, because the radius stops increasing and the temperature keeps decreasing, and you have this. Then there is, so these giants are all here, supergiants are there. Supergiants are coming out of the top end of the main sequence, and they're not completely understood at this time, exactly how supergiants form. Also, in this asymptotic giant branch, we are unsure of the exact evolution because things like mass loss, metallicity, all of these plays an effect, because all of these stars become very unstable and they start throwing out their mass. So when they throw out their mass, the whole hydrostatic equilibrium dynamics changes because that mass is now lost. Okay, and when that mass is lost, then the luminosity also, so it goes to a different point of equilibrium, and that point of equilibrium keeps changing. That's why all of these stars are also variable stars, right? Now there is a curious thing here called the extreme horizontal branch. There are some stars, in many stars like the sun, when the inside is, when the core is fusing helium, there will be hydrogen burning, which will be happening in the outer region. So simultaneously, hydrogen is getting converted to helium in the outer regions, and helium is getting converted to higher elements at the core. So sometimes what happens is the hydrogen envelope is completely expelled. And when it is expelled, what is exposed is the helium core. And those exposed helium core stars are extreme horizontal branch stars. Why do they have a higher temperature? Sorry? Yeah, this is the core region, which is fusing helium. Helium fusion obviously occurs at a higher temperature than hydrogen. And the hydrogen envelope is all thrown out. You're seeing the helium core. So that is why it is hotter. Okay. But it seems to be less luminous than this. Why is that? Core is small. So the radius of the star is small. It is hotter, but with smaller radius. Okay. And that is why it is less luminous. A more extreme example of that is the white dwarfs, which are very hot, but are very small, and therefore they are low in luminosity. So in general, radius, because it can, see, the temperature can vary by a factor of 10. Okay. And that can lead to 10 raised to 4 variation in luminosity. But radius can increase by 10 raised to 3. And that can lead to a 10 raised to 6 variation in luminosity. So therefore, radius plays a very important role in determining the vertical position of a star on the HR diagram. Okay. So there is also something known as the red clump. The red clump, which you see here very, very clearly, is caused by a peculiar stable situation wherein helium is burning in the core, hydrogen is burning outside, and the situation is stable for million years or millions of years. That nothing changes. It's in hydrostatic equilibrium and so on. And that therefore gives you a tight relationship on the red clump. Okay. Of course, this doesn't last forever, so stars will leave the red clump. Another thing to note here is that there are very few stars in between the regions. So there are stars in the asymptotic giant branch, but there are very few stars in this region. So the transition between main sequence and these giant phases of stars, it has to be very rapid, has to be very fast. Similarly, you don't see any stars. See, stars are, the sun is going to move from somewhere here to here but you see no stars in this region. That indicates that the transition from red giant to white dwarf is going to be extremely rapid. So it like just jumps here. Okay. So if we are looking at variable stars, so one can now with Gaia, we can even measuring the same flux many times. So we know which stars are variable. And so what is color coded here is the fraction of variable stars. So which stars you think, as you can see from this plot, which stars are the most variable? Red giants over here. This is the asymptotic giant branch going there. These, what are these? Extreme horizontal branch. Okay. The ones with the helium core exposed, those are highly variable. Okay. Are main sequence stars variable? They're all here. No, in general, except for some of the most massive main sequence stars. Because again, they change over strong time scales. Many of them are just waiting to jump into the giant or supergiant phase. So there is a reasonable number of variable stars over here, but hardly any below here. Okay. Okay, so let us look at one important class of variables. Yeah. Yes. What is the question? The extreme horizontal branch stars, could they become white dwarf? I have to see what their mass ranges are. Okay, but they are not. They have to see what is the essential difference between here and here. The most fundamental difference, of course, size difference is there. Sorry, huh? Convection. Temperature is not very different. Temperature is the same. Radius is different, so luminosity is different. But what is the essential difference between a white dwarf and any star for that matter? Huh? No activity in the core. There's no fusion happening here. Okay, there is fusion happening here. So it is not as if these are slowly going to become white dwarfs. They can't. They have to stop fusion. They're fundamentally different objects. In one helium fusion is happening. Here, no fusion of any kind is happening. There is no energy source in the black white dwarf. In fact, because of that, it cools like this. See, the white dwarf over its lifetime will move like this. The sun for 10 billion years will sit there without moving because of the fusion. Here, there's no fusion. It just cools. Yeah. I think any other questions? Otherwise, we can stop here and we'll take up Cepheid variables and some other kind of variables in the next class.